Hello everyone, this is Achinta Medhi. So in this video I'll discuss about temperature effect on rate of reaction and Arrhenius equation. This is the fifth video, and if you have not watched the previous videos, then links are given in the description below. Go through it and let's start this video. Today we are going to discuss about effect of temperature on reaction rates. So first of all, temperature coefficient, heating temperature coefficient. So in this case, it is generally observed that the rate of reaction increasing with increase in temperature. Okay, that means you are increasing the temperature, you will observe that the rate of the reaction is increasing. Okay, now the question is, on how much increase in temperature will increase how much rate. Okay, so it is observed that when you will increase the temperature 10 degree, okay, you are increasing 10 degree temperature, okay, then it is observed that the rate is increasing twice or thrice, okay, two times or three times. You are increasing the temperature 10 degree and the rate will increase two times or three times from the initial rate. Okay, now if you want the definition of temperature coefficient, then here it is. You can write this: the ratio of rate constants at two temperatures separated by 10 degree. This is very important. 10 degree Celsius is called temperature coefficient. You can write this definition mathematically also. So here it is: temperature coefficient Tc, okay, and it is equal to Kt plus 10 divided by Kt, and it is approximately equal to 2 to 3. Okay, that means here it is a rate constant. This is K is a rate constant of which temperature is T plus 10, and here it is a rate constant K which have temperature T. That means the difference between the temperature is 10 degree. Now I am going to write an expression which expresses the relation between initial rate and final rate with temperature coefficient. That means how with increase in temperature, how initial rate and final rate related to each other. Okay, and that is R is equal to R naught Tc whole to the power del T by 10. Okay, here R is the final rate, R naught is the initial rate, and Tc is the temperature coefficient, and del T is the temperature difference. Now let's solve a problem. So in this question, the rate constant of a unimolecular reaction is 2.66 into 10 to the power minus 3 second inverse and 2.2 into 10 to the power minus 1 second inverse. At temperature 120 Kelvin and 360 Kelvin respectively. So what would be the rate constant at 240 Kelvin? So in this question they are asking rate constant, but this expression, in this expression I was saying that it was final rate, it was initial rate, but this expression is also valid for this question. Okay, that means for rate constant, if you consider this is final rate constant and this is initial rate constant, then also this expression will be valid and we can use this expression, okay, in this question also. So it is given that, so we will write first of all this expression in terms of rate constant. So we can write, if the k2 is the final rate constant and k1 is initial rate constant, then expression will be k1 tc whole to the power del t by 10. Okay, so here k2 is this one, 2.2 into 10 to the power minus 1 second inverse, and k1 is this one, 2.66 into 10 to the power minus 3 second inverse. Okay, and the temperature difference del T is 360 minus 120, it will be 0.42. okay, this Kelvin. Now we will put these values in this equation. So here this k2 is this one and k1 will be here, that means k2 by k1. So we will write directly k2 is this one, k1 is this one, 2.66 into 10 to the power minus 3. Here it is tc whole to the power del t means this one, 240 divided by 10. Okay, so it will give you tc is 1.2. okay, next the question is what would be the rate constant at 240 Kelvin. Okay, so we will find out at 240 Kelvin. So it will be del T. We will consider any of the rate constant given here, any one, k1 or k2. We will consider this one, k1. So we will minus this one, this temperature from this temperature. Okay, so here it is. Next, del T means 240 minus 120, 240 minus 120, and here it is 0, 2, and it is 1. Okay, so next we need the rate constant, that means it is k3. Okay, and k1 it is, k1 will be, and here it is tc, and del t will be 120 divided by 10. Okay, k1 is this one, 2.66 into 10 to the power minus 3, and tc is this one, 1.2, and here it will be 0, 0, it will cut off, and here it will be 12, and it will give you 0.024, or you can write 2.4 into 10 to the power minus 2 second inverse. Next we will discuss about derivation of Arrhenius equation. So first of all we have to consider a reversible reaction, and let A is the reactant, P is the product here, and this is a reversible reaction. for in this reaction is proceed in forward. This is the forward direction and this is the backward direction. So here the rate constant for the forward reaction is K1 and rate constant for the backward reaction is K2. K equilibrium. K equilibrium comes for reversible reaction only. Okay, so K equilibrium will be attained when K1 divided by K2. Next, another term is energy change. That means del E. Del E is the energy change, and which it is equal to E1 minus E2. Now, there is a expression. This is from Hont-Hobbs relation, which express the variation of equilibrium constant EQ. This one, EQ with absolute temperature. Okay, and here it is d ln k equilibrium divided by del dt is equal to del E by RT square. It is the derivative of ln k equilibrium and it is the del E, that means change in energy. R is the gas constant and T is the temperature. Okay, absolute temperature. So we will put this value k equilibrium, that means this one. Okay, so d by d dt ln k1 by k2 is equal to E1 minus E2 R T square. Okay, so here it is. K1 is the rate constant for forward reaction, K2 is the rate constant for backward reaction. Okay, next we can write d dt ln K1 minus ln K2. Okay, and we can separately write here it is for the forward reaction and here it is the for the forward reaction, and this is for backward reaction, this is for backward reaction. So we will write separately these two things. Okay, so it will be d ln k1 is equal to E1 RT square and dt will come here. Okay, here it is dt and this part d ln k2 is equal to E2 by RT square and this dt will come here. Okay, dt, as there is a negative sign here, so both will be cancelled out. Okay, we can separately write like this. Okay, next, generally, so as this is k1 for E1 and for K2 it will be E2, so we can generalize it is. Okay, so if we generalize it will be ln k is equal to EA by RT square dt. Next we will integrate this equation, and this integration, the limitation will be k1 to k2 d ln k is equal to EA by R integration, the limit will be t1 to t2 dt and it is t square, and we can write ln k, this integration will be here k2 k1 is equal to EA by R, and when you will integrate this part it will give you 1 by t. Okay, and it is t2 and t1. Okay, next we can write ln, this, as this is the limitation k1 to k2, so we can write this part ln k2 minus ln k1 is equal to EA by R, and as the limitation is t1 from t2, so we can write 1 by, first this t2 put here in t, next minus, and as it is initially here it is a negative sign, we will also write this negative, and my 1 by, and this t1, put this t1 here, okay, t1. Understood? So from the logarithm theorem law, ln, as it is negative sign, so we can express as a k2 by k1, okay, it will become this, and here it is EA by R, and this minus minus it will be positive, so we will write first of all t1 minus 1 by t2. So this is called the Arrhenius equation. As we know, the equation d ln k is equal to EA by RT square dt. We know that this equation, and from this equation, when we will integrate this equation, we will get d ln k is equal to EA by R, and it will be t to the, as this is here, so we can write what, this t square will become t to the power minus 2, second inverse, okay, so it will be t, and here it will be a integration constant which is ln a, okay, and a is constant of integration, ln a, this ln a is integration constant. Okay, this is integration constant, and it will become ln k, okay, and here it is EA by R, and it will be minus 1 by t, okay, and here it is ln a, and when we will bring this ln a here, so we can write ln k minus ln a is equal to minus EA by RT. Next, ln k by a is equal to minus EA by RT is equal to, if we k by a, if we remove this ln, it will become here it will be E minus EA by RT. When you will remove this ln, here it will be exponential, okay, and this is the equation, and we can write k is equal to, a will be here, a e to the power minus EA by RT, okay, so this is also Arrhenius equation. This is another form, but this is also called Arrhenius equation. Okay, so in this equation, k is the rate constant, or you can say that k is the number of collision per second leading to a reaction. That means the number of collision per second, and a is called Arrhenius factor, or you can say that it represents, this a represents the total number of collision per second, total number of collision per second, and this is number of collision per second. Okay, and ea is the activation energy, that means this represents the required energy, the minimum required energy for a reaction to give a product. T is the temperature. Okay, and R is the gas constant, and the value of R is what? 8.314 joule Kelvin inverse mole inverse. Now I am going to discuss about determination of energy of activation and Arrhenius factor, and we will determine the activation energy from graphical method. So first of all, we have to write the equation, Arrhenius equation, which is log k1 by k2 is equal to minus EA by 2.303 R T2 minus T1 plus log A. You can see that this is little different from the previous equation as I have written. Okay, in this equation I have written log, and in the previous one I write ln. So as I am writing log, so I have to write 2.303, and here it is k1 by k2, so it will be T2 by minus T1. Okay, if I write k2 by k1, here it will be T1 minus T2, and if it is T2 minus T1, then here it will be a minus sign. Okay, and if we write k2 by k1, and here it will be T1 minus T2, then there is no need to write this negative sign. Okay, here where k1 and k2 are rate constant, okay, at two different absolute temperatures. Suppose T1 and this is T1 and T2 at two different absolute temperature T1 and T2 respectively. Okay, so next we will put this equation, we will plot a graph. Okay, we will plot the graph log k against 1 by t. Okay, so So here log k, and in x direction is 1 by t. Okay, and as you can see that this is log k, and this is 1 by t, and this is the intercept, that means the c constant. Okay, y is equal to mx plus c. Okay, c is the intercept, so here it will be a intercept here, okay, which is log a, and the slope is, you can see that slope is minus ea by 2.303 r. This is x, this is y, and this is the m, and this is c. So m is negative, so graph will be like this. Okay, so slope is negative ea by 2.303 r. Okay, and the intercept is log a. Okay, so slope is equal to minus ea by 2.303 r, and from this, if slope is given, and if from the graph we will find out the slope. Okay, from this line we will find out the slope, and if we know the slope, then it will be easier to calculate the ea. As this is the 2.303, we know that, and r value we know that, and slope is given, then we will find out the e. So e can be calculated. Okay, now let's discuss about physical significance of ea. Suppose this is one molecule, and suppose this is one molecule, and they are going to collide. Okay, then it will give you like this, but this product will be a minor product. Okay, but if these two molecules are in different rearrangement, like this, and they are colliding each other in a sufficient energy, okay, then it will give you this type of product. Okay, so it will be the major product. Okay, so this rearrangement prefer to have a product, and this is the effective rearrangement. Okay, so rearrangement is very much important for to give a product in a reaction. Okay, as we know that if there is a molecule here, okay, so these two atoms are molecules are bonded to each other in a energy which is called binding energy. Okay, so in a binding energy they are bonded to each other. So to break this bond, there is a sufficient energy which is required to break this bond. Okay, now another molecule is coming. Suppose another molecule is coming here, and they are going to collide, and it will give a product or not. It will depend upon the energy with which this molecule will collide to this molecule. Okay, if the energy with which this molecule will collide to this molecule is more than the binding energy of this molecule, then only this molecule will remove one of this atom from this molecule, and it will replace this atom and give a product. Suppose this one and this one, this is a product. So that means it has this colliding molecule. This colliding molecule has the sufficient energy to remove this atom and breaking this bond, and there is a formation of a new bond. Okay, that means there is a minimum energy required to break this break the parent molecule and forming a product, new molecule. Okay, so energy, that is the sufficient energy is very much important to give a product. Okay, so first one is rearrangement and next one is the energy. So this energy, this minimum energy required to break or change the rearrangement of the molecule to give a product is called activation energy. So this is the physical significance of activation energy. This is a note, and if you want this note, then have a screenshot of this. Now let's discuss a reversible reaction where there is a forward reaction where x to y, and there is a backward reaction y to x. So this is the activation energy for forward reaction, and this is activation energy for backward reaction. So to understand this reversible reaction, we have to see this graph. Okay, so in this graph you can see that this is the in y direction, energy is in the y direction, and this is reaction coordinate, and x is the reactant here. If x is reactant and this is energy for x reactant. Okay, this much energy it has. Okay, it is the energy state. This is energy state. Okay, so from here it needs this much energy, EAF. EA means activation energy, F for forward reaction. Okay, so this is activation energy for x. Okay, this is activation energy for x. X need that the sufficient energy is, this is the EAF. X needs this much of energy to cross this part. Okay, after that only it can give the product y. Okay, so this is the activation energy for x, that means the for forward reaction. Next, this is the energy for the product y. Okay, this is the energy for product y. Next, if we consider the backward reaction, this is the backward reaction. So when in the y giving this x product, then in this backward reaction this will be the activation energy for backward reaction. That means y need this much of energy to cross this energy barrier, to give the product x. Okay, so this is EAF is activation energy for x, and EAB, B means backward reaction, EAB energy is the activation energy for y for the backward reaction. Okay, and Z is the transition state. And the rearrangement at that state, when x will come through this transition state, the rearrangement will changed, or it is going to break. The bond will are going to break. So at that state it will stay for a very minute time. Okay, after that when the rearrangement will proceed and it is changed, then we will get the y product. And in the same case, vice versa, when in the backward direction, y will come through this transition state. At that state, the rearrangement of y will change, and after that it will stay for a very minute time, and after that it will give you the rearrangement of x, that means the product. Okay, now EAF is equal to what? EAF means EZ, this energy from this line to this line, Z line, this is EZ energy. Okay, EZ minus EX, this amount, this and this, we are going to write this EZ and EX. When we will minus EX from EZ, we will get this EAF. Okay, EX. Next, EAB, backward direction, we want this EAB, so we will minus this much EY, this is EY and this is EZ, so EZ minus EY. Okay, next EAF minus EAB. Okay, EZ minus EX minus EZ minus EY, and it will what? EZ will cancel out, and here it will be EY minus EX. Okay, or we can write minus EX minus EY. Okay, we can write this. So you see here, EX minus EY, this is EY, this is EX. So EX minus EY, what is this? Del H, this is del H. EX minus EY, that means del H. Del H is the enthalpy change. Thank you so much for watching this video. If you like it, please subscribe my channel and share with your friends.